sometimes, but I think both are the same.
Okay, good morning. So let us continue the lesson, but this slide that you see is important. It was in the previous lecture notes. We didn't have time to go through it. So let us actually go through it today. This is properties of definite integrals. So this means that we learned about Riemann sums, upper sums, lower sums, and then we learned about the notion of integrability. And this in principle should come immediately after that. So, for example, this is very important to know all of them. So, f and g be continuous on an interval containing the points a, b, and c. Then, for example, integral from a to a, f of x dx is 0. Okay? So, it's good to motivate them. For example, if I have integral from the a to the same point a, if f is continuous, of course, here it doesn't matter, okay, so because this is just at one point, so it becomes 0. Is that understandable? Why? There are two ways to understand this. Do you remember it has some connection, this integral has some connection to area? Yes? So make sure that I am recording it. Yes. So this has some connection to area, so in principle, if I write integral from a to b f of x dx, we learned that it has some connection to the area below a curve. So if I have a function which is continuous on the interval from a to b, for this case, let us consider that this is always above the x-axis. I will talk about areas in the next module a little bit. But here you have the intuition that this area, if it is above the x-axis, can be calculated using this integral. And of course, then if it is going from a to a, it means that these two lines are the same, so the area is 0. There is no area left there, okay? But that's just an intuition, yes? Integral from a to a means I start from a, when I go from a to b, where b is greater than a, I just cover some part of the region. So there is an area, not 0, associated with that. But if I go from a to a, I have just only one single line, so this means that there is no area. That's of course intuition. But if I want to talk about it a little bit more rigorously, how can we say that? A is equal to a here, but in principle, do you remember, if this function is continuous, we had this before, that the function is integrable. And if it is integrable, it doesn't matter which Riemann sum I actually consider for calculating this. And then let us, for example, consider the regular partition with upper sum, for example. So if I have this f, and then I have a regular partition with n parts, do you remember what was the definition? The definition was sigma m, the maximum or the supremum, and k delta xk, k goes from 1 to some n, yes? But I am considering the regular partitions because of Archimedes' Riemann theorem, it is enough, yes? So this means that delta xk is delta x, and indeed is b minus a divided by n. And of course, if a and b are the same, so what happens? This becomes 0 identically for all of them. And then it means that every upper sum is 0. And for the same reason, every lower sum is also 0. And it means that if I take the limits of those sequences, this becomes 0 at the end. So yeah, that is a little bit more rigorous way of actually motivating us. The other thing that was a little bit surprising for me, Adams, the writer of the book, author of the book, takes this as a theorem, but this is usually should be defined as a definition. So he says that, okay, if we flip these two, then it becomes negative of itself. Yeah, I would rather to put this as the definition. So he is claiming that, okay, if I replace a and b, what happens? B and a will be replaced. So every delta x will be negative. So then I will pick up an overall negative value. Which, it's not very good, because do you remember delta xk was the length of the kth interval. And the length in principle cannot be negative. So most of the books take this as the definition. So if you have integral from 1 to 3, it's normal. But if you see this symbol somewhere, it's a little bit odd. This is defined to be integral from 1 to 3 with a negative sign. So don't forget to put that negative sign there. Okay. And let us see what is the next one. So the next one is just this combination. If you want to prove it, it becomes a little bit lengthy. So this means that this is a linear operation, integration. So I can just pull the constants out and decompose my integral to two parts, as we had for the case of primitive functions. And the next one is also very important. So you can break an integral to different parts. So for example, if you have integral from a to b, f of x dx, I can go from a to c, f of x dx, provided that I add another term to it in which I go from c to b. So finally I have to go from a to b, yes? F of x dx. Okay. Yes?
Does any restrictions on that? Like, does the function have to behave a particular way in those?
No, well, for this theorem we are considering that because I have written on top that f and g are continuous.
Okay.
Yes, because otherwise, of course you know that there are functions that are not continuous but is still integrable. But we're not talking about those things right here. That much. I have one examples in the lecture notes and I put this as an optional that if you want to see this.
So integral of like tan x from 0 to 2 pi wouldn't be a thing.
Yeah, we will talk about that. That will come on the topic of improper integrals.
Okay.
Because here this is called the Riemann integral. In the Riemann integral, I assume that my function is bounded. The book starts with continuity, but we can relax that continuity for the time being. We can start with boundedness. And we also need to have a bounded interval. So in the next module, we'll learn more or less a little bit rigorously that what happens if we relax one of these two conditions or both. Yes? So the tangent function between 0 and 2 pi is not bounded. So that's called a generalized or improper integral. But for Riemann integral, we have a function which is bounded, and I am working on an interval which is also bounded. Yes? Yes?
Does she have to be in between A and B?
Yes, that is. I just wanted to address. No. If you accept this definition, there is no restriction. But of course, if you want to understand it from the area point of view, you usually consider C to be between. For example, if I have this graph, and let us say A is here, B is here, and C is somewhere in between. Okay? So if I want to calculate the area from A to B, I can calculate area from A to C and consider it area number 1, and then calculate area from C to B and consider it area number 2. And now if I want to find the total area, it's clear that I add them up. But of course, for this intuition to work, C should be between A and B. But there is no restriction for C being between A and B. For example, if you want, I can integral from 1 to 3. I can go from 1 to 2, and then I can go from 2 to 7, and then I can go from 7 to 3. Yes, that's possible. So I can break the integral as in any number if I want, and there is no restriction. Okay, the next one is that's also important. This is something you need to know. So if a function f is less than or equal to function g on the same interval, what does it mean? It means that when you are restricting yourself between a and b, the graph of f is below the graph of g. Is this notation I used? Yes. So for example, if I have this one, this is the graph of f, and then I can draw the graph of g like this. For example, I don't know, something like that, and it can go down, okay? So this is graph of g, this is f, this is g. So at least in this interval, what you see that the graph of g is always above the graph of f. So that is the meaning of f being less than or equal to g. Is that right? Then of course, what is the claim? The claim is that the integral of f can be at most integral of g. Why? At least in this picture it is clear. Integral from a to b f of x dx will be less than or equal to integral from a to b gx dx. From area point of view is very clear because this integral represents this area below the graph of function f, but this will represent the area below the function g. And of course, if the graph of g is above, the area that it covers is greater than the area that the other function covers. Is that clear? From an area point of view, it is clear. Can you see it a little bit more rigorously? I mean, that is not a mathematical proof, that's an intuition. But if you want to do this theorem rigorously, it is possible. Even at this level, you can see that. So if I compare the upper sums for regular partitions, one for f, for example, and one for g. So I pick one partition, one regular partition for this interval from a to b, and then I construct the upper sum for f and the upper sum for g. Okay, what do you think the relation will be? Because this f less than or equal to g, it means that the values of the function f are less than or equal to the values of the function g. And here when I write, it will be m, let me put an f up there, k and delta x sigma. This means the maximum of the function f on the kth interval. But then if I want to write this upper sum, I will have something similar, but this will be the maximum in kth interval of function g, and then the same delta x. Yes? And I hope that you agree that if f is less than or equal to g, the maximum of f at any interval cannot go beyond the maximum of g on the same interval. So this means that delta x's for each interval, for the kth interval, the delta x's are the same, and it is clear that the maximum of f in the kth interval cannot go beyond the maximum of g in the same interval. So this means that the upper sum here and the upper sum there, the upper sum here is term by term smaller than the upper sum there. So this means the sum will also be smaller than sum. So understanding this from, this is the proof, but you have to make it rigorous if you want to write the proof. Okay, so this doesn't mean I have to have this intuition of area, so this should be independent. So is that clear? Okay. So for example, the other one is called triangle inequality. That's also good to know. So if I have integral from a to b, absolute value of f of x dx, no, the other way around. Absolute value of integral from a to b f of x dx is less than or equal. If I flip the absolute value to the integrand, so let me write it properly. Absolute value of integral from a to b f of x dx, you know that this is a number. I am allowed to take absolute value. And then I can take the absolute value from my function first. It becomes a new continuous function. And then integrate the new function again. It gives me another number. Is there any relation between these two numbers? First integrate, then take absolute value. First absolute value, then integrate. Yes, this one is always less than or equal to the other one.
Wow.
Yes? Yes, that's clear. That comes from the previous theorem. So let me see if I'm recording it in the correct way. Yes. So, why is that true?
Absolute value of f of x is always greater than or equal to f of x because f of x is either equal to absolute value of f of x or is negative.
Yes. So this means that any function f of x for every x cannot go beyond its absolute value, cannot go below negative of its absolute value. Yes, that's very clear. And then according to this theorem, because this one is smaller than that one, the integral of this one is also smaller than the integral of that one. And because this one is smaller than that one, the integral of the left one is also smaller than the integral of the right one. So this means that the integral of this one is sandwiched between two positive and negative numbers. So it means that the absolute value should be also smaller than that. It's good to do these exercises yourself because I want to continue. This is the last lesson in this module. But I just want to tell you that you can have this motivation using the Riemann sums. Okay, there are two other important rules that I want you to know. And they are very, oh, by the way, this is not in the book, but I think it is good to know. This is also true. So if I have a continuous function, this is, by the way, important because of what is coming. If I have a function f, and then if it is continuous on a closed interval, so definitely you will know that this function has a minimum and has a maximum. So let me call little m the minimum, and let me call the capital M the maximum. So it is guaranteed for every x chosen here, f of x is greater than or equal to m, is less than or equal to m. Yes? And then we just learned that this is a constant function. You can consider this as a constant function, as a constant function. So the integral of a to b of that function, dx, should be less than or equal to the integral from a to b, that function, f of x dx. It should be less than or equal to the integral from a to b, that function dx. Yes? That's exactly this theorem I am using 2 times. One between m, little m and f, and one between f and capital M. Yes? But now, do you remember we had one theorem, one example, that I told you that if you have a constant function, the constant function is integrable, and we were also able to use Riemann sum to calculate this value. Do you remember what was it? It was this constant multiplied by b minus a. And the same is true here. This is this constant multiplied by b minus a. So that is the inequality that you can see in this slide, yes? The value of the function, the value of the integral is always between this times b minus a, the minimum times b minus a, and the maximum times b minus a. And it is also understandable, yes, from graphical point of view, what is the meaning? For example, if I have this function, a, so what is my minimum here? So little m, I hope that you agree, this is little m, okay, and then here is b. So what is the meaning of m times b minus a? b minus a is this length, m is this length. So if I multiply them, what happens? I am calculating this area, the area of this rectangle. And the area of this rectangle clearly is smaller than the area below the curve. And the area below the curve is nothing except this integral. So from geometrical point of view, all of them are simple. And then if I take a maximum, I make another rectangle, but clearly the area of that rectangle is bigger than the area of the below the curve. Yeah, so these are understandable. Yes?
Could another way to prove this theorem be that you can do upper and lower sum, but with just one partition, which is just a to b?
No. One partition will not be enough. Here you mean, can you repeat? Because I mean for integrability, one partition does not work. You should prove that the upper sums for all partitions go. The best we could do is that relax all partitions and only restrict ourselves to regular partitions, but not just for one single partition.
Oh, I mean, sorry, I think I mixed up my words. Let's say we take a regular partition, but in the partition we only have 2 values, which is just a and b. And then
No, integrability does not come even, I mean what I'm saying is that you should have a sequence of infinitely many upper sums and take the limit.
Yeah.
Yes? It doesn't work.
Okay.
Yeah. So you should have a mechanism that you have a partition, but you should be able to increase the number of points in the partition. And if that limit goes to a number, and for the same happens for the lower sum, and these numbers are the same, then you can say that the function is integrable. Yes?
Yeah.
Okay. So now, these are 2 other ones, these are very important. If you have a function which is odd and continuous, you really don't need to calculate the integral at all if it goes from minus a to a. So it means this is very tricky. Sometimes it helps you a lot. Okay? And it happens for the even function. If you have an even function, do you remember about odd and even functions? So what was an odd function? An odd function was a function whose domain is symmetric about 0. Moreover, f of minus x becomes minus f of x. This is odd. And then even was that f of minus x goes back to f of x itself. So this is even. But the domain should be symmetric. It means that if x belongs to f, to the domain of f, then minus x also belongs to the domain of f. This is what we had before. Okay? So now this is claiming that if your integral is a particular case, not from a to b, from a negative number to its positive. Okay? In other words, the interval is symmetric with respect to the origin. And then if you have an odd integrand, a function which is odd is sitting as your integrand, you don't even need to calculate the function, this is 0. If the function is odd and continuous. The counterexample, if it is not continuous, is this one. For example, this function, is it odd or even? It is odd, because first of all, it is not defined at 0, but it is defined symmetrically around 0. And then, if I change x to minus x, what happens to my function? The function becomes minus the function. So this is an odd function, and this is symmetric. But if you say, I am using this theorem and the answer is 0, that answer is wrong. We will see why in the next lesson. Okay, so be careful. Continuity is very important here. If it is continuous and odd, and this is symmetric, you can immediately answer this is 0. Okay, if I have time, I will come back to it. Otherwise, you should think about using Riemann sums, not upper sums and lower sums, to justify why this is true. It's not very hard. Justify. I don't want you to write rigorous proof. And then the same, something similar for even functions. For even functions, it is not as simple as that, but what happens, it becomes 2 times the integral if I go from 0 to a f of x dx. So for example, for even functions, it is very easy to immediately realize that. Yes? So if I have an even function, what is the property of the graph of an even function? It is symmetrical with respect to the y-axis. For example, if I can draw a symmetrical shape here. Okay, and then if it is from minus a to a, so you see that when I go from minus a to a, I am covering this area and that area. That integral means the total area. But because of symmetry, you can see that this area and that area are the same. So if I calculate one of these areas from 0 to a and multiply it by 2, I will get the total area. For this one, if I have an odd function, what will happen? If I have an odd function, it is continuous, it definitely passes through the origin, and it is symmetric with respect to the origin. And now let us say that I go from minus a to a. But I want you to, this is a graphical way of understanding it. It would be very instructive if you also think about it as in the Riemann sum term. And if I have time, I will come back to it. But can you see that this integral should be 0? Yes? Because first of all, if I go from minus a to a, I am covering this and I am covering that. Okay? This area is below the x-axis. It is negative of the integral. And if this area is the same size area, but it is above the x-axis, so it becomes the positive integral. So when you add them up, they will cancel out. Okay? The reason that is a little bit mysterious because, by the way, do you know that this integral should be negative? Yes, because that is exactly this theorem. If the function is negative, then the integral of my function is what? Is less than or equal to the integral of this constant function. Yes, and that's 0. So this integral should also be negative. So if the function is below the x-axis, the integral is negative, the other one is positive, but the values are symmetric because the size of the areas are the same. So this is the justification why this one is also correct. But you can also think about it as Riemann sums, not upper and lower. Think about Riemann sums, and then you can have a rigorous way of understanding. Any questions so far? So these are all the things you need to know about these integrals. Okay, so here we want to talk about the mean value theorem. This is probably the most practical lecture, which is very useful for the exam. all the content here is something that you need to know very well. So the mean value theorem for integrals and the first and second fundamental theorems of calculus. So this is essentially what you really need for most of the questions in the exam or this lecture. Okay, so the mean value theorem for integrals. So what is the mean value theorem for integrals? You see it on the slides, but let me see. Yes. So this time, I just write it here. You can see the exact theorem there. So if you have a function f, and you have a closed interval a and b, and you know that f is continuous. Okay? Then what is it claiming? It claims that there exists a c in a and b such that if you calculate the integral from a to b f of x dx, which definitely exists, why? Because I'm assuming that f is continuous, so it is integrable, such that this integral becomes f of that c multiplied by the length of the total interval. Yes? That is what is claiming in mean value theorem for integrals. Do you remember we had another mean value theorem for derivatives? F of b minus f of a divided by b minus a equals to f prime of c. That was called mean value theorem for derivatives. But it is easy to understand why this is true. I mean, because I want to do some of these proofs because I see some of the exam questions include the proofs. Okay, at least for these cases. So how can I prove this? It's very simple. The theorem is the one I want to use this fact. Yes? So what I will do, I would say that because my function f is continuous on the closed interval, min-max theorem guarantees that there is a max and there is a mean for this function. So this means that the existence of little m and m such that f of x lies between them for all x in a and b is guaranteed. Yes? Min-max theorem. Yes? But now, according to what we learned up there, I can immediately conclude that m times b minus a is less than or equal to integral from a to b f of x dx is less than or equal to capital M times b minus a. So I am using that property of the integrals. But then, it's very easy, you see. I can divide by b minus a, and can you tell me why this will be useful? First of all, I am allowed to divide by b minus a without any problems because b minus a is positive. So I will not be worried about if I have to change the sign. No, I just divide safely. I get this. Yes? This is a number. Integral is a number. When you divide it by b minus a is also a number. But this number is somewhere between the minimum value and the maximum value. Do you remember any theorem regarding that? So if I have a function which is continuous, let us say this is the minimum value of my function and this is the maximum value. My function starts from here, goes continuously, for example, and then I have it a and b. So let us, yes. And then I have this is the maximum value. So this means this number, I don't know what this number is, but I know it's somewhere between m and little m and capital M.
Intermediate value.
Yes, intermediate value theorem guarantees the existence of a number, yes, between them. So it is switched. So if this number, so let me call this one L. This number L is somewhere here, for example. Yes, this number. And then it is guaranteed by intermediate value theorem that there is a C here, which is mapped to L. Yes. Yes.
If we just take the derivative on both sides, isn't that just a normal mean value theorem?
No, because taking the derivative, we haven't studied that yet. We haven't studied how to take the derivative of a definite integral. We learned to take the derivative of indefinite integral. How to calculate, that is the topic of the first fundamental theorem of calculus.
Okay.
Yes. So that is the only reason that I am bringing this up, because if you want to deduce that theorem, you have to go in this logical way.
Okay.
Yes. But anyway, is that understandable? So L is this number. I don't know what that number is, but it is guaranteed it is between M, and because of intermediate value theorem, intermediate value theorem, this means that there exists a C in A and B such that what happens? This f of C becomes L. Yes? But f of C, L is this number, integral from A to B f of x dx, and I have divided by b minus a, then I multiply by b minus a. So f of c b minus a becomes equal to the integral from a to b f of x dx. So again, I am not telling that I know what c is, because I don't. I know the existence of such a c, that when I calculate f at that c and multiply it by b minus a, it becomes exactly the value of my integral. Yes? So remember which theorems we needed here. So max-min theorem was used. Intermediate value theorem was also used. Combining these two and combining that with that theorem from properties of integrals, we were able to prove the mean value theorem for integrals. Okay? What is the geometrical interpretation? Yes?
If we have some function.
So let me make it a little bit simple. So let us draw a simple curve here for you. So then I want to listen to you. So A and B.
Yeah, and we take the area under it.
Yes, why area? Because this integral is the area below that. What is the meaning of this geometrically?
It's the area under the curve, or what do you mean?
No, what is the interpretation of the whole theorem geometrically?
Oh yeah, there is the function at some point passes a value such that if you draw a horizontal line, the area of that rectangle will be the same as the area.
Exactly. So for example, if we agree with this theorem, which we have to because we proved that, it means that there is a C somewhere here. I don't know how to draw it, but hopefully around here. I'm not sure. So if this is C, this will be f of C. And if I ask you what is the meaning, geometrical meaning of f of c times b minus a, I hope that you agree with me, this is the area of this rectangle that I am right now constructing. Do you agree?
Yes.
The area of this rectangle is nothing except f of c times b minus a. Yes? And this integral is what? Is the area below the curve. So this means that you can find one c somewhere, so that when you construct this rectangle, the area of the rectangle is precisely the area of the curve below the curve. So for example, I don't know if my shape is a good shape or not. So if my shape is precise, it means that this part that I have extra for the rectangle will be compensated for this part that I do not have it in the rectangle. So it means that you can always fine-tune a C so that the area of this rectangle becomes exactly, not approximately, exactly to the value of the area below the curve. Is that yes?
Does it have anything to do with Riemann sum? Because we also kind of get somewhere in the middle.
I haven't thought about that. So I haven't thought about in that way. So I was able to use Riemann sums and everything to formalize those ideas, and using those ideas combining with the previous ones.
Okay.
Might be there are some ways, I don't know. But one thing is clear, there is one definition for f of c. This is called the average of the function. I want you to know, because it is also in the book. So f of c is called the average of your function on the interval. And this is usually denoted in your book. They put a bar on it. And then they put an interval here. This means the average of f on the interval a and b is defined to be f of that c. But what is f of c? F of c is this number. So this is why you don't see f of c in the book, you see this formula in the book. So if I give you a continuous function and I give you a closed interval and I ask you find the average of my function on that interval, what you do, you just simply integrate it from a to b and then divide it by the length of the interval. So that's called the average. This is the definition of the average. Any questions? Okay. So now let us go to the first fundamental theorem of calculus. It's extremely important part here. So let me read it for you. So let I be an interval containing a, and let f be a function that is continuous. I have written it in red on I. The function A, capital A, usually we call it the area function, defined on I by this formula is differentiable. Oh, that is a mistake. It should be differentiable. I will fix it. It's a typo. It's differentiable on I, and the derivative of it is equal to f of x for every x in I. Okay, so it's a little bit subtle theorem. I want you to understand that. And I want to try, first of all, this is one of those theorems I want to prove for you because I have seen that they have asked it in the exam. But before doing that, let me intuitively understand what the problem is telling you. So let us consider a closed interval. Yes. And let me give you a function f, which is continuous. And because there are different letters involved, as you see, x and t, so let me draw my diagram. Instead of calling the horizontal axis the x-axis, if you don't mind, let me call the t-axis, and then let's keep it y as it is. Okay, I want you to understand, have a good feeling about this. If I write a to b, what is this at the end? Let us say that you know how to evaluate this integral and you do the calculation and you give me your answer. What is your answer? Is it a function? Is it a number? What is it?
Area?
No, what is it? I mean, is it a number or what?
A number.
It's a number. Yes, it gives you a number. Yes, but what is the meaning of this? It means that you have a function y equals to f of t, and a is fixed here, b is also fixed somewhere here, and this gives you the area, as you said, which is a number. But now, let me keep a fixed, but let me take b as a variable so that can move around. Okay? So instead of fixing it at b, let me not fixing, just take it as x. But x can vary. And then it means that this will be x. So you see that this is still a number, but that number depends on the value you choose for x. Is that right? Because if I make x smaller, the area will be smaller. When I make x bigger, the area becomes bigger. So this is somehow a number, but it is a function of this x that I put in. So it is this is a function of x, and because this is related to the area, usually people call it the area function. I want you to understand this is a function, because if I give you x, any x, and of course b should also be somewhere here. I am not allowed to go beyond b because the continuity is guaranteed on a and b. So as far as I am on the right domain, this is a number, but it is not fixed. For every x it is fixed, but when I start changing x, I am changing the area, so I'm getting a function. When I get a function, I can talk about everything that I could talk about a function, including the derivative. Yes?
You can use the same idea if we switch places a and x.
Yes, we will come back to that, okay? But what I wanted to justify is that what I have written is a function of x. So it makes sense to talk about the derivative of that function. Yes? It's a function, so I can talk about the derivative of that function. Now, the question claims that the derivative of this, what you need to do is to switch your integration variable with this x up there, and you get f of x. That is the claim of the first fundamental theorem of calculus. If you have a function which is defined through an integral in this very particular way, and if this integrand is continuous, what you need to do is just to replace the integration variable with that x, and that's the derivative of your function. Simple as that. Is that idea clear? Okay. We want to prove it because I have seen that sometimes they ask to prove this question. Okay, so can you help me? We want to prove it. If I want to prove it, do you remember I want to prove that the derivative of a function is this one. And this is not in my table of differentiation. So there is only one way for me to start from scratch, meaning the definition of the derivative. So let us start from definition. What is the definition of derivative? Do you remember? It is the limit of ax plus h, do you remember? Minus ax divided by h goes to 0. Okay, but because of technicalities, if you don't mind, let me calculate. So here is a, here is b. It doesn't matter that much. Let us see if it matters. Okay, this is the definition of the derivative. But now I want to go forward. So this means that the limits, let me go a little bit slowly here. H goes to 0. I have a minus sign here. Ax is clear. Ax is this integral. So I put it up there. So this becomes integral from a to x, f of t d of t. But can you tell me what is this one? What is a of x plus h? It means your input is x plus h. If my input is x, it appears here. Now that input is x plus h, it also appears there, but it becomes x plus h. So this becomes integral from a to x plus h, f of t dt. Do you agree? But then, let me write something and ask your opinion. I copy and paste the first one. But I would write it plus. Can you tell me what I will write in front if I write plus? I have to reverse them. I just learned that if I reverse them, it picks up a minus sign. So it becomes from x to a. Yes?
Okay.
But can you combine the integral, two integrals in the numerator into one integral now?
Yeah, like really.
Yeah, exactly as we had on top of that. So it goes from x to a of the same function. Now it goes from a to x plus h. So I can combine them into one integral, which goes from
X to
x to
X plus
x plus h. X to x plus h, and then the function ft dt divided by h goes to 0. So far it's very simple. Yes? The next thing I want to use this intermediate value theorem for integrals. Okay? So, according to the intermediate value theorem for integrals, what can I guarantee? I can guarantee the existence of a c in between these two numbers. Okay? I don't know if x plus h is bigger than x because h might be negative. When h goes to 0, it might be a little bit smaller than 0 or bigger. So it is not, I cannot write definitely between, because if I write it in that way, I am taking this for granted that this is bigger. So I would say there exists a c between x and x plus h such that, okay, can you complete it for me? I'm using this theorem. So let me review it. There exists a c in your interval such that f of that c multiplied by the length of the interval becomes equal to your integral. So this means there exists a c between x and x plus h such that my integral is equal to what? F of that c, yes, multiplied by the length of my interval, which is x plus h minus x. Yes? Okay, but now I have put in a space here. Do you think this is this c, it is a constant, but you know that if I change my x, because I am changing the interval, this c might also change. So c in principle depends on x. And this is why I left it open, so this is also c of x. So it is a number. It is between x and x plus h, but because x is not fixed, I want to let them vary. So this number depends on the choice of x that I started with. Is that right? Okay, and then how can I continue? So this means that the integral from x to x plus h, ft dt, is equal to f of c of x, and this one is just simply h. And now what I will do, I will put it back into my formula and continue. So let me clean this. Let me start from here a little bit. Okay, so I continue here. So this means that the derivative of a prime of x, I calculated the derivative up to here, and then I stopped, I did something else, now I bring it back and put it here. So what happens? This becomes the limit, the denominator is h goes to 0, but instead of the numerator, I just put this expression. Yes? F of cx times h.
And
Yes.
simplify.
Yes. And then h's are cancelled. So what happens for me is a little bit strange because I have to calculate the limit of c of x as h goes to 0. Okay? Because if I wanted to be more precise, this does not, it also depends on h, because you know that c is between x and x plus h. But for example, for concreteness of discussion, let us consider that h is positive here. If h is positive, then c of x is between x and x plus h. If x is negative, if h is negative, I have to write it the other way around. It doesn't change anything. Yes? But now, can you tell me what is the limit of c of x and h, to be honest? I have to write it properly. H goes to 0. What happens? What is this limit?
You found x? No.
Because the limit of the left does not depend on h, so it remains x. The limit on the right becomes
X.
x. By sandwich theorem or by squeezing theorem, the limit of the middle one should also be x. Okay? And then we had a theorem that the function is continuous, okay, and this limit exists. So I can flip the limit into the function and say h goes to 0. So it's a very bad notation from the very beginning because you don't see the dependence on h. Sorry for that. Okay, so then it becomes f of x because this limit is x. Okay? So this is more, yeah, you have to be careful about what I wrote here. So in principle, you should write it as c of x and h. Not only depends on x, but also on h. But here my limit variable is not x, my limit variable is h. So here is a squeezing theorem. So you see how many theorems are involved so that you can get the answer to this. It is good to see it once. Any questions? Okay, but I told you that I have seen it only one or twice. They have asked me to prove it. But most of the time, there are questions that you are supposed to use it. Okay? And that is not always as simple. I want to give you other versions as well. But if you don't mind, let us have a break now here so that I can have time to clean the board and then we can continue. So 5 minutes break. Thank you.